In the following graph describing the probability distribution of molecular speeds for the noble gas elements helium, argon, krypton, and xenon, which curve represents krypton? And the answer is B. This light blue curve right here, that's krypton. Let's discuss probability distributions and we'll see why this one is krypton. The distribution being referenced in this problem is the Maxwell-Boltzmann distribution of molecular velocities. And it's given by this complicated equation right here at the top right. I'll blow that up for you. So here's the equation that describes the Maxwell-Boltzmann distribution of molecular velocities. And it says that the probability that a gas particle has a particular velocity is given by this expression over here to the right. We're not going to analyze this in too much detail, but notice that the probability that gas molecules have certain velocities depends on both the mass of the gas particle, highlighted in green, and the temperature of the gas, which is highlighted in orange. Let's take a quick look at these two factors that the velocities depend on. First, the temperature. So if you graph this equation for a particular gas at a particular temperature, you get these hump-shaped curves. The probability that gas particles move with certain velocities versus the velocity, so that's your y and x axis. Here is the probability on the y-axis, that velocity on the x-axis. The distribution is given by these hump-shaped curves. And I've drawn gases at two different temperatures. A colder gas at 300 Kelvin is indicated by the blue curve, and a hotter gas at 500 Kelvin is the orange curve. There are two things you want to notice about these curves. First of all, the peak of the curve represents the most probable velocity. And notice that the peak of the blue curve is at a lower velocity than the peak of the orange curve. So that tells us that hotter gases, the most probable velocity is faster than the most probable velocity for colder gases. Another aspect of the curve that you want to notice is the shape of the curve. The area under the curve you could think of as representing all of the gas particles. So focus on the blue curve. Think about this colder gas and look at the area under the curve. If you could take a pair of scissors and cut this curve out, cut out that hump-shaped region, that would represent all of the gas particles. Suppose there is a mole of gas particles, and this piece of paper that you would cut out represents that one mole. And we're interested in gas particles that are moving with velocities between v1 and v2. So this little portion of the x-axis. So how many gas particles are moving between v1 and v2? Well, that would be represented by this sliver right there. Underneath the curve, that sliver right there. Now, if the entire area under the curve represents a mole, then how much would be represented by that sliver? If you could compare that, maybe that's about 1/10 of the entire area. So maybe about 1/10 of a mole right there, okay, between V1 and V2. So that's how you kind of quantify the probability. So about 1/10 of the particles would move between V1 and V2. Now, if you compare the hotter gas, then looking at its area under the curve, if you could cut out that orange area, then how many gas particles move between V1 and V2? Well, that would be a smaller sliver compared with 1 mole of gas, which would be the entire area. Then this smaller sliver looks about half the size of the larger blue sliver. The smaller orange sliver is about, it's a lot less than that blue sliver. I would say if the blue sliver is about 1/10 of the gas particles moving between these velocities, then the orange smaller sliver would say be 1/20. So out of 1 mole of gas particles, only 1/20 of them would be moving with velocities between V1 and V2. So for colder gases, you're more likely to find gas particles moving with slower velocities. Now for hotter gases, notice that over here at larger velocities, the orange curve lies above the blue curve. So if we're interested in, say, velocities over here between this point and that point, if you can imagine similar slivers being cut out, the orange sliver would be greater than the blue sliver. So that's a maybe more complicated aspect of the graph. And if that makes sense, then great. If it's a little too much, then maybe watch the video again. But at the very least, just remember that hotter gases move faster. The gas particles move faster than colder gas particles. The other thing to remember for probability distributions, and one which will help you solve this problem, is the mass dependence. Here are two curves representing xenon and helium. Now, xenon, I'll blow this up a little bit. Xenon is the heaviest gas particle out of these 4 noble gases, and helium is the lightest. Xenon's 131 atomic mass units per atom, and helium is 4 atomic mass units per atom. And I'll remind you where you can find out the mass of the gas particles. It's right on the periodic table. So xenon is over here. We're talking about the noble gases, and if you blow up xenon, you can see that it's 131 atomic mass units per atom. And helium is the lightest one. It's only 4 atomic mass units per atom. And that's where you find out how heavy the gas particles are. And remembering that the probability distribution, the probability depends on the mass. And if you plug in larger masses, then the probability that they have that particular velocity is affected. So going back here to the mass dependence, looking at the curve for xenon versus helium. Now xenon, the peak is over here to the left, and helium, its peak is over here to the right. So we could say that xenon, the gas particles move more slowly than helium. And you could also discuss the areas under the curves and compare the slivers, and you can see that for faster velocities, the helium gas particles are more probable to move with faster velocities than the xenon particles. Now, so that's between xenon and helium, and you can see that helium, the gas particles move more quickly than xenon, and that's because they're much lighter than xenon. So what about all 4 of these noble gases? Finally, let's see where krypton falls into place. Now going back to the periodic table, the noble gases, they increase in mass going down. So you got helium. The next one in our list is argon. That's heavier. That would move more slowly. Krypton would move even more slowly, and xenon would be the slowest. So I tried to to draw this curve. So this curve right here, I've tried to draw the same graph down here, and we're interested in this light blue curve. Here, let me move this up a little bit. We're interested in the light blue curve, that one right there. So we're not interested in the slowest gas particles and not the fastest ones. We're interested in the ones that are moving second to slowest. Okay? Now, we can get that information directly from the mass of the gas particles. So helium, being the lightest, at 4 atomic mass units per particle, would move the fastest. That would be this curve with its peak over here to the right. Xenon, with the heaviest gas particles, would move the slowest. Its peak is over here all the way to the left. But krypton is the second to slowest. So that's the one that we're interested in. We're not interested in the slowest, but the second to slowest. So that would be krypton. And that's how you solve this problem. And maybe too much information on the Maxwell-Boltzmann distribution, but I hope it was helpful.